in various science and technology areas. So this is hosted by the Ministries of Earth Sciences, Ministry of Science and Technology, CSIR, and various government organizations, ministries. The purpose is to forge partnerships between government and industries of focus areas and to draw upon the rich expertise and competence of leaders of both science sectors who have significantly contributed to the economic growth of the nation. So we are having a variety of programs in this iConnect events, and this particular event is on climate change through the lens of modeling, artificial intelligence, and machine learning. And we know climate change is a reality. It has been affecting the 2021 Nobel Prize also came in for climate science. We also had the release of the IPCC AR6. So climate change is real. It is affecting all the components of the Earth system, the atmosphere, the ocean, the cryosphere, biosphere. And so the attribution to climate change, there's a very strong global and regional attribution of the human influence, how human activities have affected the climate system. And this comes because of mainly the models, the Earth system models or the climate change models. And so at a global scale, we do understand, we are able to attribute the influence of human influence on climate change and also make future projections. What will happen to the climate system and what are its impacts of climate change on the different components of the Earth system and the natural systems in the future. And this is important for policymakers. It is also important for developing applications, for example, hydrological applications or agricultural applications, renewable energy. And also it's very important for the policymakers. So at a larger scale, we do have some good understanding. The modeling of the climate change signals are robust. But when we come to regional scales, there are challenges in the representation of the physical processes because it's a very, very nonlinear system, highly nonlinear system. They're all interacting on different space and time scales. How to represent these nonlinear physical processes in the models has been a challenge. So this particular session is going to focus on how to improvise the climate change modeling and also bring in new techniques. Now we have a huge amount of data from the satellite. It has provided very insightful information. How to make use of this data that coming from in situ data and also the satellite data. Can we improve some of the key physical processes in the model and improve the climate change projections? And using new techniques like the AI/ML, and which are gaining a lot of popularity, and they're being applied in a variety of applications. And so with these ideas, this program has been developed. And this topic this session will focus on climate change modeling, key scientific challenges, use of AI and ML and deep learning applications for Earth system modeling, climate downscaling, also GPU computing, and also crop yield forecasting. These are some of the, and we have also brought in not only the scientific people, also some people from the industry. And we have a very eminent set of speakers and panelists, all young people. And so I will like to quickly introduce them. We have Dr. Ayantika De Chaudhary. She's a senior scientist at IITM Pune. She works on monsoon dynamics, climate change, and she's been actively involved in the development of the IITM Earth System model. And she also analyzes all the satellite data of precipitation, extreme precipitation, and so on. And she has incorporated the aerosol module in the IITM ESM. And so she will give the opening aspects of the climate change. What are the regional issues related to the monsoon? And we have Manmeet Singh, Dr. Manmeet Singh, a very young and very dynamic young colleague. And he is involved in climate change modeling, and he has got a very strong expertise in AML. In fact, I depend on his advice on many things, many aspects of AML for weather and climate science. He has also worked on the effect of volcanic aerosols on the monsoon and the ENSO coupling, and he has done very interesting work. And we have Ankit Agarwal, Dr. Ankit Agarwal, assistant professor at IIT Roorkee. Ankit is basically a hydroclimatologist. He has done excellent work on extreme events using complex networks, and he knows how to apply these data-driven techniques for modeling extreme events. And so we are welcome Dr. Ankit. And we have also Dr. Manish Modani from NVIDIA. Manish Modani is a principal solution architect at NVIDIA and is a thought leader in HPC and HPC-AI domain. And so we welcome Dr. Manish, especially not what he will be contributing in terms of the GPU computing, which is going to be very important for AI/ML applications. So we are having him. And Dr. Advai Mitra is a researcher from IIT Kharagpur. He works also on machine learning and data mining. And he has applied this for downscaling of the climate projections and to understand very complex spatio-temporal processes. And so we are happy to welcome him as a speaker at the iCEN-56. And we have other panelists. Dr. Swapna Panikal, very senior scientist at the Center for Climate Change Research at IITM Pune. She was the main person leading the IITM ESM activity. She has got strong expertise in oceanography, and she was responsible, played a major role in coupling the IIT, in having this coupled model for the IITM ESM. And our expertise is in sea level changes, and she is also IPCC lead author in the AR6 assessment. And we have Shaktivel Sami, Dr. Shaktivel Sami from NCPOR, and he has strong, Dr. Sami has strong expertise and interest in scientific database data mining applications, and particularly with regard to use of these techniques for the polar regions, because polar regions, both the Arctic and the Antarctic, they are not only seeing rapid changes in the cryosphere, but also extreme events. So Dr. Shaktivel Swami will be talking about that. And we have Professor Sridhar Balasubramaniam, who's a professor at the IIT Bombay in climate studies. And his expertise is in fluid mechanics and mechanical engineering. And he's also expert in weather and climate analysis modeling. And he's a co-founder of Weathercast. And we are very, very happy to welcome Professor Sridhar Balasubramaniam. And finally, Dr. Praveen Pankajakshan. He's the Vice President for Data Science and Artificial Intelligence at Cropin. And he leads the data science and machine learning with Kortava AgriScience Hyderabad. And this is very, very important, linking the climate change issues and for practical applications such as agriculture and use of these novel techniques. So we are very, very happy to welcome him as a panelist in iCEN-56. And with this brief introduction, we will go to the presentations. I understand that we have 4 speakers, but 2 of the panelists have also requested that they would like to make presentations. I think so. We will be basically having 6 presentations and then followed by panel discussion. So with this brief introduction, now first I would like to welcome Dr. Ayantika Chowdhury to give her presentation. Dr. Ayantika.
Thank you, sir, for giving me this opportunity to speak. So I'll just share my screen.
Yeah.
So is it?
Yeah, it is. Yeah, it is visible. Okay. Yeah. Yes, I think.
Yes, sir.
Please.
So, basically the talk today, my talk is based on process-based improvements in climate models. So to understand, is the slide okay? So to understand climate change using a climate model, so we first need to understand the formulation of a climate model. So a climate model has all the components of the Earth's climate system. So we have the atmosphere, the air that surrounds the Earth. We have to model the oceans, the lakes, the rivers, that is the hydrosphere. We have the land surface. We have the ice sheets, the glaciers, which is the cryosphere. So this integrated system basically constitutes the climate model. Now, the formulation of the general circulation model is based on the governing principles of atmospheric flow, which is the horizontal momentum equations, that is from the Newton's laws. We have the thermodynamic energy equation, which gives us the energy conservation. Then we have the mass continuity equation, which gives us the conservation of mass. Then the atmospheric flow is assumed to be in hydrostatic balance, and also we have the moisture equation. So these equations, they form the dynamical framework of the model. Now, the right hand side of the equation shows terms like friction, Q, the heating, and moisture source and sinks. So these terms are basically derived from the physical processes, and they are parameterized in the model. And the primary errors in the climate models, they arise from deficiencies in formulation of these terms. So when we form the from the equations, we solve these equations to predict the rate of change of temperature, pressure, velocity, moisture, etc. And we solve them on grid points. So we represent the atmosphere as discrete grids in three-dimensional grids, horizontal and vertical, and we have the temperature, wind, moisture, pressure on these grid points. So when we have a finer grid, we have more number of grid points. When we have a coarse grid, we have less number of grid points. And typically, say we have 10 variables, we need to solve the equations for 10 variables and say 100 levels. So we have around 10 million equations to solve for a particular time step. And also the integrations has to be solved in smaller time steps, say about 10 minutes. As we evolved in time, as we progressed in time, these climate models has gone to higher resolution. So in the 1990s, say we had 300-kilometer resolution, but the present day models are around 100-kilometer resolution or even less. So we have maybe 50-kilometer resolution on in the present day models. Also, the vertical levels have increased. So now we have around 60 levels or more. And on the boundary of these atmospheric models, we have coupled the ocean general circulation model, which in itself has horizontal and vertical resolution on all the oceanic processes. And for different components, also we have coupled different types of models like the land surface model, ecosystem models. So the entire climate model is an integrated system, which is generally known as an Earth system model. So the equations are solved in using finite difference scheme to predict the change of the variables. Now, within the grid space, the physical processes that are going on has to be parameterized. So the different physical processes are not explicitly resolved because they are at a higher resolution than the model resolution. So we need to parameterize them. We need to formulate them based on the large scale variables that we receive from at the grid points. So the most challenging issue has been the parameterization of convection clouds. So we have different types of clouds. We have deep convection, deep clouds. We have shallow convection, which gives shallow clouds. We have warm rain processes. We have ice processes. So a multitude of process goes on into this convection and microphysical parameterizations. Also, we have radiation. We have the incoming shortwave radiation, the outgoing long-wave radiation, which is basically the radiation that is emitted from the Earth's surface. This interacts with the atmospheric gases like carbon dioxide, water vapor, ozone, also the aerosol particles which absorb and scatter the radiation. So that radiation is parameterized based on these interactions. Then we have at the surface, we have the flux exchange, which is the latent heat, sensible heat fluxes from the land surface as well as from the ocean surface. Ocean waves and currents are also parameterized. So there are a lot of processes in all the different components needs to be parameterized, and if the parameterizations are not accurate, then this leads to uncertainties in the climate projections and climate prediction. So let us take an example of the Indian monsoon. So we know that the Indian monsoon occurs in a very unique geographical region. We are bound in the south by oceanic, so the oceanic processes are very important. To the north, we have the Himalayan mountains, we have the entire continent, so we have the land surface processes. And this large-scale circulation, this flow from the ocean is due to the land-sea thermal contrast. It converges over the Indian region and it gives rise to deep cloud system, the large-scale organized convection, which produce copious amounts of precipitation over the subcontinent for 4 months. So we know that predicting seasonal prediction as well as climate prediction of these monsoons has been a very challenging problem. And these latent heating that is released from these cloud systems, they drive the monsoon circulation. So basically the monsoon is set up by the thermal contrast, but the latent heat released from these very deep clouds, the clouds can be as deep as 8 kilometers. So these deep clouds, the latent heat, enormous amount of latent heat that is released from these clouds, they maintain the monsoon circulation. And within this large-scale monsoon circulation, we have different types of precipitating systems. So we have systems like the synoptic systems, like the monsoon depressions, lows. We have metropospheric cyclones, as well as we have this northward propagating organized rain bands, this large-scale organized rain band which propagates from equator towards the Indian subcontinent and gives rise to the active break spells. And within these precipitating systems, there are various types of precipitation processes. Now, parameterizing these precipitation processes and associated latent heating has been a grand challenge for prediction of monsoon, seasonal as well as climate prediction of monsoon. Now, to understand the processes from observations, we can actually partition the precipitation into different components based on the microphysical processes that goes on inside the clouds. So we have the convective precipitation. The radar echoes are very strong in this region. This consists of young active convection, where the growth of particle takes place by accretion, by rhyming, and the vertical velocities in this region are very high. So depending on the microphysical processes, the latent heating from the convective type of rain, from the convective precipitating systems, is maximum in the mid-level. So this is the vertical profile of latent heating. We see when we have convective type of precipitation, the latent heating is maxima at around 5 kilometers. But when this young convection grows old, the microphysical processes gets modified. The particles grow by vapor diffusion, and there are gentle upward motion, and the heating profiles are very different. So for the stratiform type of rain, we have a heating profile which is maximum in the upper troposphere and a cooling profile in the lower troposphere. Now, these different types of heating profile would generate very different type of circulation. So it is very important to properly represent this type of processes or the latent heating in a model. So let us take a look at how the partitioning of precipitation occurs over our monsoon region. So from the TRMM observations, which has a precipitation radar on board, we have been able to extract the information of the vertical structure of the clouds and partition these precipitating systems into stratiform and convective precipitation over the Indian region. So we see, so the top panel shows the rainfall during the, hello. So the top panel shows the precipitation during the monsoon region. So we see that the monsoon precipitation consists of stratiform as well as convective rain. So extract the information of the vertical structure of. So the convective rain is basically dominated over the foothills of Himalayas, whereas we have more stratiform rain over the central India. So there is a difference in the occurrence of the type of precipitation. So there will be a difference in occurrence of type of heating. The vertical level of heating will be important. So now how do we know that this different vertical level of heating is important for our monsoon circulation? So we can use a simple general circulation model to understand this problem. So this is an example from the active monsoons, wherein we have a lot of rainfall over the Indian region. So we find if we take the circulation anomalies during the active monsoon.
4 minutes. 4 minutes.
Okay. Okay, sir. So during the active monsoon, we have this large scale circulation anomalies over the Indian region. And when we take the precipitation during the active monsoon, we see the presence of different precipitation structures like the stratiform and convective cells. So we need to represent these processes within the general climate models to get the flow. So from a simple model, what we did was we introduced a variation of stratiform and convective rain within this monsoon region, and we found in the right panel shows the vertical variation of heating as we introduced stratiform into the system. So the heating got elevated, and when we observed using this general circulation model, we find that when we have more convective system, we have a localized circulation in the mid levels. With stratiform, the circulation in the mid level intensifies. But what happens in an atmospheric model where it interactively calculates parameterization? The different parameterization schemes are found that it cannot produce the vertical variation of heating. It leads to large errors in the model heating in the model levels. So this gives large errors in the heating distribution, which drives an erroneous circulation and gives it's challenging for us to give accurate prediction of monsoon. Now, as we evolved from CMIP 3 to CMIP 5, if we look into the biases of monsoon precipitation, this panel here shows the green here is the bias, that is the dry bias over the Indian region in CMIP models. So from CMIP 3 to CMIP 5, CMIP 6, if we go, we see the magnitude of bias has reduced, but the large scale extent of the bias still remains in the climate models. So these biases in precipitation and the biases in latent heating, it leads to biases in large scale tropical circulation, which eventually leads to biases in the sea surface patterns. And these sea surface patterns again leads to biases in precipitation. So, so there is a vicious cycle of bias which propagates across all scales and all components of the Earth system model. So there is an urgent need to reduce this precipitation bias in monsoon and tropical precipitation. Now, how do we reduce this systematic bias in a model? So we can use ultra high resolution cloud resolving coupled ESMs, but this is very computationally expensive. We cannot run it over the entire globe for a longer time. So the other alternative is, in the recent years, we have this AI/ML techniques, and we can use these techniques and the data available to improve our models. So studies have shown recently that these machine learning approaches can use the data from different sources, the in situ observations, the satellite observations, and they extract the patterns and give us insights into the physical system. So the deep learning methods can gain a process level understanding of Earth system problems and help us predicting the seasonal and climate projections. So the future of the Earth system model is basically in a model data fusion, wherein we use this high gridded observational data, we incorporate it and we develop the model, we reduce the uncertainties from the model and give a better projection of the climate and its impacts on society. So I would like to summarize by saying that there is an urgent need to improve the CRE process in climate models. So the uncertainties from climate projections is basically originates from the processes that needs to be formulated. Like for monsoon, we have this organized convection, cloud system, latent heating, which leads to errors in coupling of the circulation, large scale circulation and convection. We have other warm rain processes, etc. Now, how do we approach this problem? We can go into very high resolution modeling, that is kilometer scale modeling, but that requires high computational powers. And then we have the model hierarchies, like we use a simple model to understand the process, then we improve the process in a higher resolution model. And also we can take, there is a view, we can take a balanced approach, like we combine the theory, model and observations to gain a better understanding and improve. And finally, with the new developments of machine learning, deep learning, we can extract the patterns, we can understand the problems using data, a lot of data that is available. So we can conclude by saying that the climate projections can advance by harnessing the observations and modern computational capabilities systematically. So we need to use new methods from data assimilation, inverse problems, machine learning, and make it possible to integrate these observations and targeted high-resolution simulations in an ESM and use both to quantify and reduce the uncertainties. Thank you.
Thank you, Dr. Ayantika. We will take the questions later on. Actually, along with me, Dr. K.C. Gowda from the CSIR Fourth Paradigm Institute is also coordinating this event. So he will be taking the question answer sessions. And welcome, Dr. Gowda.
Yeah, thank you, Professor Krishna.
Thank you. Sorry, I missed in the introduction.
No issues. Good morning, all speakers and panelists, as well as viewers.
Yeah, thank you, Dr. Gowda. And one more point, a lot of focus has been given in this particular on the IITM ESM, and the speakers and panelists are from IITM. This is because one of the reasons is the IITM ESM is the first model from India that contributed to the CMIP6 projections and the IPCCR6 report. So we have already a basic framework. So the idea is how to improvise this. This was the basic intention, the way it has been organized. So I just forgot to mention this in my introduction. Yeah. So now I would like to welcome Dr. Manmeet Singh to go ahead with this presentation. Dr. Manmeet, please.
Thank you so much, sir. Yeah, I'll just share my screen. Is my screen visible? Hello.
Yes, Manmeet. Yeah, it is visible. Yeah.
Okay. So good morning, everyone, and welcome to. So thank you so much to Dr. Krishnan and for giving me this opportunity to speak at iCEN-56. I'll be talking about deep learning augmented numerical weather prediction. Now, deep learning for deep learning for weather prediction is a lot of different studies have tried doing on a regional perspective. So we have the numerical weather prediction models, and deep learning when it started picking up computer vision somewhere like 10 years ago. People started using convolution neural networks, LSTMs for time series, but that was all either at a location specific in a location specific context or in a limited region or domain. But for the first time in 2019, for the first time in 2019, Jonathan Wayne et al. And Dale Duran, this group in University of Washington, they talked about whether machines can learn to predict weather. They typically use the spatial map, the global spatial map, as an input to a UNet. Now, UNet is an image-to-image regression model, and what they did was they took the geopotential height at 500 hectopascal and temperature at 850. So these are separate models. They took the input at time t, and the target was at time t plus 1, and they used what is known as the ECMWF, European Center for Medium Range Weather Forecasting, ERA5 reanalysis product, and they talked about developing a fully autonomous data-driven weather prediction system. And this is once trained, it becomes like a fully autonomous thing, wherein once you have the output at time t plus 1, it can go in again back into the model, and the long integrations can be performed. So they showed the performance of this model DLWP with IFS 42, IFS 63, and it was comparable. But and they showed at different lead time, although comparable, but still the dynamical models were better than the DLWP. Next, in 2020, what they did was the convolutions are happening on a 2D image. So the library, the frameworks that we have, TensorFlow, PyTorch, And basically the problem that is most concerned with the computer vision community is 2D images. So all these libraries, they consider 2D convolutions, although spherical convolutions are there, the operators are there, but it's still not very easy to implement them in PyTorch or TensorFlow. So and the problem is that if we project a spherical, so the Earth is a sphere, and if we project it on a 2D plane, then over the poles the area is different, and over the tropics it's different. So performing, like assuming them to have the same area, if we perform 2D convolution, will introduce spherical distortion errors. So in 2020, what they came out with this a modification of DLWP. They call it DLWP CS, DLWP cube sphere, wherein the global spherical data is transformed into a cube sphere, which has 4 faces along the tropics, 2 faces along the poles. Now, each face of this cube sphere can be approximated as an image. Now, you can see here when it is unwrapped, so it looks like this. So 4 faces along the equator, 2 along the poles, and now this becomes as like all the faces are having an equal area. And what is performed here is, so for example, the green one is a face of the cube sphere. So typically in a unit, the to maintain the input and output image size to be same, we generally pad with zeros in dog classification or a cat classification problem. But in a cube sphere framework, what they proposed was that they would not pad it with zeros. Rather, they would pad. So, for example, this edge, this edges. So the from the bringing the data from the adjacent edge. So there would be communication of the data in the entire global domain, and this would facilitate the learning. The model will learn the large scale teleconnections as well. For example, El Nino and monsoon, the drought teleconnection is very strong, although El Nino occurs in the Pacific, monsoon is a system over India. So now this they use this for temperature at 850 hectopascal, the and geopotential at 500, and so I've already discussed the prior studies to this, the Wayne et al. Work, and there is still a challenge in this kind of this kind of framework that they said. One is that the, like, temperature at 850 and geopotential at 500 are relatively easier as compared to the precipitation and soil moisture. These are, so temperature and geopotential, these are predominantly the prognostic fields in the dynamical models, whereas precipitation and soil moisture are the diagnostic fields. They are derived from the computations of the dynamical field. And if we go in this kind of a pure data driven framework, we are actually throwing away the advancements in the numerical weather prediction that have taken place in the last so many years, and NWP has been undoubtedly been a success. So there is a need for a system for global precipitation forecast, which can be considered as a digital twin of the real system. So what we did here was, so as a first step to show as a proof of concept, just took the ERA 5 reanalysis temperature and total cloud cover and different fields as input, taking one field as an input, global field, but in a cube sphere framework, cube sphere mapping, and the global precipitation as a target. So in this proof of concept, so here I'll show. So we use the data from WeatherBench. WeatherBench is nothing but it is derived from ERA 5, but the data is made in such a way that the data science community can very easily access it and can use it for the data driven model. Now, in this, we used the total cloud cover, developed two models, total cloud cover as input, precipitation as target, surface air temperature as input, and precipitation as target. So the results, so I'll show some results. So this is the median of 1 day precipitation. We also did the linear regression, and DL1 is the model from total cloud cover to precipitation. DL2 is from the temperature to precipitation, and these are just at the same time step from error 5. And we also took the GFS, the operational short range forecast model that is running at IITM. And so this is the ground truth. So median for DL1, DL2, and GFS and ground truth, they look similar. Linear regression is really bad. And then we performed the grid point correlations for the period 2012 to 2015, because I got the data for 2012 to 2015 for the GFS model. And although DL1 and DL2 are not exactly in a forecast framework, but still at 1 day correlation. So at 1 day integration of the dynamical model, we can consider the inputs to be as good as the initial conditions. So we can see that in this type of framework, the grid point correlation, wherein it is in the GFS, it is it is improving substantially in DL1 and DL2. So then we computed the different important land areas, the grid point mean of the grid point correlation, and next, so that was just the proof of concept. So next is the actual development of the product, I would say, in which we have for which we have shown for the short range forecast of global precipitation using deep learning augmented NWP. So why we are calling it deep learning augmented NWP is because we are taking the input from the North American multimodal ensemble CFS V2 hindcast. So CFS V2 is operationally used in different parts of the world, and this hindcast that are available on the on from IRI from 1982 to 2010. Every 5 days they will start an initial they will start a simulation, and which will the data is available up to 10 months. So what we did was we extracted it for 1, 2, and 3 day lead times, and this was the input. The target is the era 5 precipitation, and so so the precipitation and temperature at 1, 2, and 3 day lead time as an input, and corresponding era 5 precipitation at 1, 2, and 3 day as the target. So we first transform this into a cube sphere format. Then the unit training is performed, wherein in the input we have the CFSV2 temperature and CFSV2 precipitation, and in the target we have the era 5 precipitation. So here, since this is a cube sphere format and this is not a standard unit, this is a unit in which the faces are sharing the data amongst each other. So the teleconnections, the model is learning those kind of nonlinear relationships, and then once we get the forecasted or the predicted precipitation in the cube sphere mapping, we transform it back to the latitude longitude grid, and we perform the evaluation on the output. So we take the training data from 1982 to 2000, the validation from while training. So we are constantly monitoring the loss, and so that overfitting does not take place. So validation is from 2001 to 2002, and the test data is from 2003 to 2010. Now this is a baseline that we have considered. So this paper was published in the year so by
Manmeet, you have
yes,
3 minutes.
Yes, sir, I'll finish. So, so this is from the short range system at IITM. The iMerge, iMerge. This is the climatology. This is the day 1 forecast from the model, day 3, day 5, and day 8. And these are the biases. So we can see that over India there is a positive or wet bias at short range timescales from the CFS V2 model. Now we did a similar plot from the deep learning minus era 5 and the NWP, that is the NMME CFS V2 hindcast that we have used. This is the average bias in the JJA. So we are getting somewhere like similar around 10 or more than 10 millimeters per day bias over India at lead 1, lead 2, and lead 3 in the NWP dynamical model. Whereas in the deep learning model, we can see that there is substantial reduction in the bias, and so this we also check for September, October, November DJF, and March, April, May, and then we also check for the specific cases. So this is the South Asia, so the Mumbai heavy rain event on 26th July. So the CFS V2 initial condition starting on 25th July. So lead 1 day is 26th July, lead 2 is 27th July, and lead 3 is 28th July. So this is the era 5. This is our model deep learning augmented NWP, and this is the CFS V2 forecast. So we can see that at least in the spatial pattern, there is a substantial improvement in our model. And although there are some issues with the magnitude on which we are still working. So we checked for other cases as well, like Myanmar cyclone Nargis, then Hurricane Katrina in 2005, Hurricane Ivan in 2004, China floods 2010, then Central Europe floods in 2010, and these are the metrics for the spatial maps that I just showed. Now, in the ongoing work, what we are doing is we are extending this up to the present day. So we are using the MS Web the data for as the ground truth, because the era 5 is good. It is so it is it's better than any other reanalysis for precipitation. But so we are using MS Web, and it uses the largest number of gauges worldwide at till date, and the data is available from 1979 to present. And corresponding to that, we would use the hindcast from MSWX, so which is available as 3-hourly 0.1 degree global data at from 1979 to present. And they have compared. So this paper recently came out around 1 or 2 months ago. They have compared it with the ECMWF seasonal product, and it's they're showing that the accuracy is much higher than the ECMWF product. So I'll just conclude by saying that framework for fast and reliable global forecast have been prepared. So just like Dr. Ayantika was talking, there are biases in the model. So we have used deep learning to try and improve or to reduce the biases in the dynamical models. And we are also working on extending this framework to process-based improvements in the climate model. So using the latent heating profiles and improving the processes, physical processes in the climate models, so that we can get improved predictions in the climate scale, as well as so in general the dynamical models improve. So that's all I have for this presentation. Thank you so much.
Yeah, thank you, Dr. Manmeet. We'll take up the questions later on.
Thank you.
Now I invite Dr. Ankit Agarwal to give his talk on network techniques for hydrological applications. Dr. Ankit.
Thank you, Dr. Krishnan. So good morning to all. Dr. Krishnan, please confirm. Can you see the screen? Is it visible?
Yes, yes. Yeah, it is. Yeah.
Okay, it is in the presentation mode now.
Yeah, it is very, very clear. Yeah.
Great. Morning to all. Thank you very much, Dr. Krishnan, for inviting me to this wonderful session. I connect climate change through the lens of modeling. This is Ankit Agarwal. I'm assistant professor in Department of Biology, IIT Roorkee. So thanks to Dr. Avantika and Dr. Dr. Manmeet, who have set up this space. The stage is already set up. Dr. Avantika was talking mostly on the physical modeling, which is physics-based modeling, which is very important. Dr. Manmeet really talked how AI/ML can really cater the need. I'll be talking mostly how do we handle the data set, to bring out much more information. And my lab, which is at the bottom, hydroclimax, decomposing the complexity, says a lot. So we try to really handle data in a different way so that we can bring out much information. And this talk today, network techniques for hydroclimatological application, will show some example on it. So let's understand the hypothesis. I will show two hypotheses and then some application. That's all in 10 minutes I will be we all have handled the time series. Yeah, it could be anything, hydrology or climate or seismic signals and all. And we all agree that this time series, whatever the time series we handle, has a different component of frequency in it. For example, maybe this green time signal you see has a frequency of 2.5, 5 hertz, 10 hertz. Yeah. Now the argument is that you can get much more information from this signal if we can basically filter out or basically decompose different frequencies in different time domain. So for example, this monthly update data, which could be rainfall, which could be stream flow or sea surface temperature, I have just segregated different frequencies in it in the time domain. And how do I do it? I use the wavelet. So basically, wavelet allow me to decompose the time signal into various proxies corresponding to the signal. So this is my first argument. And if I do that, what do I get? So again, you see a time series which has different frequencies and different time domain. So basically, I can localize, I can enable the frequency localization time. For example, there might be a signal corresponding to 4 to 8 of periodicity existing only half of the period, initial period, which might be because of seasonal cycle, or 16 to 32, which may be an cycle which is existing throughout the time cycle, and another which may be on a decadal scale, which is existing only half of the time in the later stage. Yeah. So the idea is that one time series has embedded a lot of signals. We just try to separate it out to understand the process in a very scale specific manner. So this is one hypothesis. And why do I do it in the climatology? Because I know there exist different information at different scale. What do I mean by this? For example, climate process observed at finite time scale carries the influence of processes occurring at coastal time scale. Let's understand by a simple example. Any rainfall process occurring on an event scale, 1 day scale, carries the dynamics of a seasonal cycle. In turn, the seasonal cycle carries the influence of the long-term cycle, decadal, multi-decadal. So we basically, this is why we do this in the climate side. Okay, what we understood so far in the time domain, wavelet can handle the time domain. How about the spatial domain? There comes, because in the spatial domain also exists information at different scale. A simple example is the Google map. Let's say when you zoom in and zoom out, you get different information at different time, different spatial scale. So for the same, we use the complex network technique, which is the new paradigm, which is the emerging technique, which is very simple. I would say what this complex network means, there's a collection of nodes, and these nodes are the stations where we get the information. This could be pixels in the satellite data. This could be regrid data, grid points. This could be the real station data where we have automatic weather stations or seismic signal, yeah, the stations. And then we connect them through some links. And what are the links? So for example, this picture shows, and these links we set up by some similarity measures. The simple one, we all know correlation, event synchronization, mutual information, entropy, like any similarity measures we use to find the similarity between these two stations, the two grid points or the two pixels. Yeah, basically how they share the information. For example, these all are the stations in India, and then you see, and the resultant network we call the climate network. Yeah, so this is active area, very active research area in climate and other disciplines. It's a powerful tool because we can have a spatial data representation, data visualization, and the best thing is that, as I said, decomposing complexity. Because let's say if you have a 10,000 station, the 10,000 to 10,000 pairwise connections, we don't need to analyze all the connections. We can just reduce, and we can just keep maybe a 1% of the connections. So you are reducing the billion of the connections to the, let's say, 1,000 of the connections, and then analyzing the same thing. So this is the very beauty of the complex network. Let me still give you a example. How do we create a network? We have 7 stations. Okay, very simple. We have 7 time series. What we do, we just find a similarity based on anything, depending on your data, whether you have the Gaussian data, non-Gaussian data, you have event data. So we applied some similarity, and we just got the pairwise similarity. But we don't want to keep all these points. Yeah, I'm not interested in the 7 into 7, 49 connections. I'm only interested in the strong connections, the very strong connection. And I apply threshold, which is always subject dependent, the requirement, what connections I want. I want the real extreme connection, I want moderate connection, so on. And then now, instead of 7 into 7, 49 connection, I only have 6 connections here. So this is my climate network, at least for India. This is one example just to understand how. So using these two arguments, using these two hypotheses, we have proposed various methods in our group. The very two methods I'm showing is the multi-scale event synchronization, which has been published in 17, and we have seen so far a range of the applications. Yeah, people have even used in the heartbeat, in the medical, they are using it in the. I have also seen people citing or using the method in the geophysics, geotechnical signals. Another, we have proposed wavelet multi-scale correlation. And even very recently, we have also proposed wavelet multi-scale entropy. So various methods we are proposing based on this concept, because the method is very general, simple. So now, if this argument is clear, the hypothesis is clear, the methods, I'm not going much on the method side. Let me just show you some application, very clear application. So this is a simple, what we have taken 10,000, around 10,000 time series into 2x2 grid. For the sea surface temperature all over the globe. Yeah, and then what we have done, we have just identified the pairwise similarity between them and plotted the 95th percentile. When we see this picture, we already are very happy because we already can see sort of some. Here it is highlighted. Okay, we already see some, for example, we already see some, sort of some patterns here. For example, we all know ENSO pattern, IOD, non-Atlantic oscillation. But when we go on multi-scale, when I decompose all the time series, that is 10,000 time series, and calculate the pairwise similarity on different time scale, the picture really becomes clear. Yeah? Because we are working on the anomalies on all the finer scale, that is less than annual, I do not see any observation, or I do not see any patterns, because we are working on the anomalies and we have removed the annual signal. But when I see on this 18 to 60 month, this particular scale, I see two highly correlated regions are emerging. One is in Eastern Pacific and another in the Indian Ocean. And we all know that this might be the Indian Ocean and the Eastern Pacific interact via the atmosphere. Interestingly, on 16 to 32 months, this pattern get prominent in the in the Eastern Pacific and Indian Ocean. And we all know that this ENSO, this might be the ENSO, which interact at 2 to 7 year cycle and might be visible here. Another important patch which you might be seeing here in the Southern Ocean. Right now, we do not know whether this Southern Ocean is connected to ENSO or it is connected to Indian Ocean. I don't know, because this figure is not able to give such information and why such connections are emerging. So what I know from this is 16 to 32 months, the connection between this Eastern Pacific, Indian Oceans are strong, and which might be because of the atmosphere. What I see on the 30 to 64 months, if you see the next scale, 30 to 64 months, the region of the high correlation in the Eastern Pacific is fading away, but coexist with the spot of high correlation on the Northern Pacific, forming together a pattern known as PDO, which is in the warm phase since 1970. And with the period of cold phase, this variability is forced by Rossby waves and also can be seen in our analysis. Now, one of the interesting thing also, and the same scale, what we also see, the spot of high correlation around subtropical North Atlantic that becomes prominent on the next scale. It resembles the SST pattern that are linked with the North Atlantic oscillation via atmospheric and affecting SST. So what we are claiming, basically, you understand the scale specific. We all know ENSO influences the Indian cycle, but where and how. So that scale specific information could be seen. Now, if I say, it is also important, if you see in this figure, to note that subpolar North Atlantic and subtropical North Atlantic are positively correlated, which is a known response of ocean surface temperature to NAO. So this scale specific information we brought out using the network technique and using the scale. So many, I mean, this figure is interesting, has served a lot of information which could be validated, but still the visualization is missing. I'm not able to understand which region is connected to. For example, the region in the North Pacific, this well-known ENSO, is connected to themselves, the grids are connected to themselves, or they are connected to Indian Ocean. So what we have also done, we have plotted the 3D visualization plot. This was we did in the supercomputer cluster at Potsdam, because they had this big tool, was difficult to. So now, as we said, on the smaller scale, the finer scale, the connections are the smaller one, because it is by the Dobler's first law of geography, which says that the nearby points are connected, well, densely connected. We ignore them because this is the interesting scale. So 18 to 60 months, we said the two regions, Northeastern Pacific and Indian Oceans, are densely connected via atmosphere. We see the long range connection, which is of the range of 20,000 kilometers. I have removed such plots, but it's in the paper in the scientific report. Now this is scale, this is the region which I was saying we don't know yet. So this region in the Southern Ocean. So a link between SST in the Southern Ocean to ENSO event via southern annular mode, that is the north-south movement of westerly winds that encircles Antarctica. Because this figure, now we are very sure this region is not linked with the IOD, but rather with the Eastern Pacific ENSO region, and this is the north-south movement of the westerly wind. One other important observation we see from this figure is that not all the teleconnections are via atmosphere. There are teleconnections which are via the oceans. For example, the lot of connections which are going from North Atlantic to Southern Oceans. This shows a lot of connections. Yeah, this is the seesaw response that is due to transport of heat from Southern Ocean to North Atlantic via Atlantic meridional overturning circulation, AMOC. And we know that if AMOC is stronger, more heat is
Dr.
transported.
Ankit, you have 2 minutes.
Yes, I will. So you have more heat is transported to the northern ocean, which is causing warming in the more Arctic than Antarctica. So this is all such phenomena could be revealed. We also worked on Indian. I will basically skip. But I mean, Dr. Krishna is also part of it. We also see how these are linked to it. Now I will just end up with one very strong application which we are just exploring now. So whenever as a hydrologist we work on the stream flow, we are dependent on the meteorological variable. So this time we are basically skipping all the local drivers. We are directly linking with this indirect drivers for the stream flow variability, and we got very interesting results. So this is the Germany, because we have the very good data for Germany stream flow. These are the well-known three regimes, alpine regime. Let me show you what we got with this. So this is the alpine regime, and what we want to see, can you really see how the stream flow in this region is governed by this long-range processes, this outshore processes. And we got very interesting reason. One is the North Atlantic tripole, which is basically, and we also know physical reason why this is happening, because North Atlantic tripole is densely very strongly linked with the NAO, which basically influence the westerlies and which is responsible to bring a lot of moisture to this region. Yeah, so and such connection could be directly revealed by this process. Another is this Baltic and Linguid, basically this region. This is a Mediterranean region. This is also known as the 5D weather system. Maybe weather system which takes the lot of moisture and take us to the Europe, and because of the Alps, they shed the moisture. A lot of stream flow is basically linked. So all these connections on different scale, basically you can see this is the positive and this is negative connection, and which scale they are happening. This is also very revealed. So a lot of the ideas that could be you can also work on the stream flow and also methodological things. So if I say I can conclude, we are proposing as a group, we propose various advanced spatial temporal methods. They are very general. They could be applied in different domains, where interactions of the multiple timescale exist, geoscience, ecology, economy. We have shown the application of physical temperature, because climate forcing affects weather at large distance. We have also linked with the stream flow, because this could help in the prediction, and we have compared to the other models, this multi-scale model could perform, are robust and could perform. So with this, I conclude here, and this is our special issue open in Spanish journal. Maybe some of you is interesting. I will be happy to answer. So thank you very much, Dr. Krishnan. Thank you very much.
Thanks a lot, Dr. Ankit. Dr. Sagar Gade, I think there is a lot of noise coming from here. So please mute it. Mr. Sagar Gade. Yeah. So thank you. So now we move on to the next speaker, Dr. Manish Modani, on the use of GPU computing for AI/ML applications. Dr. Manish, please.
Good morning. Thanks, Dr. Krishnan, and to giving me opportunity to speak here. Hope I am audible and my screen is visible.
Yeah, screen is visible, baby. Yeah, it's fine. It's fine. You're able to see this.
Let me start with 1 minute video and then we'll start here. Hope it is audible, sir.
Yeah, it is. Yeah.
ये लो खाना।
अरे चाची, इतना सारा खाना, पर आपके हाथ का अचार गायब।
धूप निकलेगी तभी तो अचार तैयार होगा। भगवान जाने इस मौसम का, बार बार छत पे भागते रहो, एक यही काम रह गया है मेरा।
आपके घुटने कैसे हैं चाची?
अगर ऐसा मौसम रहा ना तो एक दिन ये भी खत्म हो जाएंगे।
मेरे पास एक इलाज है चाची, ये देखो।
फोन पे?
हाँ, धूप कब निकलेगी मतलब आम कब सुखाने हैं, सर्दी कब पड़ेगी मतलब घुटने कब बचाने हैं, ये सब आपके फोन पे।
ये सब तुम्हें कैसे पता है?
मेरी कंपनी है ना, उसका ऐप है ये। मौसम से हम सबको फर्क पड़ता है चाची। पता हो मौसम कब बदलेगा तो हम कई चीजों की तैयारी कर सकते हैं, आपके अचार की भी।
अरे वाह, तू तो कमाल का वेदरमैन निकला।
Weather is a hidden layer of insight that can predict how we feel and the decisions we make, the foods we crave, and how and where we satisfy our appetite. We drink more fizzy drinks when it rains and eat more yogurt when it's windy. Indoor paint sales increase when there is above the average wind. Hand and body lotion sales increase when there is no cloud coverage. Auto gas sales spike when temperatures are colder than average. Arthritis and COPD can increase on specific days. You can get an advance.
So hi, the objective of this video to show that I can act also, right? So this is a video shot in when I was in my previous work, company, weather company. I was in IBM before joining NVIDIA, and this is to show that now with weather and climate, the different use cases are evolving. The need to have the more accurate information about climate or weather changes or what is upcoming, that helps in various segments and various industries, right? And that's where the previous video what you shown, that is from weather company, and weather company is one of the use case of NVIDIA GPUs. There they are able to run their model at 3 kilometer resolution. They use MPass model, which they call as a graph, and they run at 3 kilometer resolution, and then data being further interpolated at 500 meter resolution. And that's how all users get on their, and they get all the information through app as well as all the data sets they get. And those data sets being used in different segments. The beauty of that model is not only resolution, there is an hourly update of that model, and that is possible because of they run their model with the accelerated computing, which is GPU enabled system. They run on that system, right? So with that, I would like to start. Thanks for my previous speakers, all set the need and the reason for required for further improvement and why AI plays key role in this segment. So in my talk, I will talk about how the what NVIDIA is doing in this domain, how the NVIDIA platform is enabling various kind of implementation of deep learning algorithm in the data simulation to modeling every stages. And then in end, I will talk about 1 or 2 slides where we are focusing more and where you will see that more things are publishing with NVIDIA, right? So with that, let me start with the little background that earlier, and it's a common tendency, we need everything faster. If today something is taking say 1 hour, tomorrow we expect that should finish in 50 minutes and so on. And that's where the things started with GPU. Earlier, the CPU processes, they were from 1990, they were there, and every year their frequency used to get increase, and the automatically speed up was there for each model. So every year 1.5x performance. But around 2005 time frame, that speed was stagnant due to energy requirement and the size of the system, motherboard and all. There was a constraint, chip size was constrained. So then it is kind of stagnant after 2005. Even with the high frequency system, they start running on lower frequency, and there was no speed up in the any modeling or any computational what we do on systems. Around 2005, before that, NVIDIA was known as a graphics company since 1993. But in 2005-6, we came up with the CUDA, and which enabled to use this graphics card for number crunching. And from there, the journey started for accelerated computing using NVIDIA GPUs. And now we are seeing the performance gain, approximately 1.5x per year. That is the combination of new hardware innovation as well as the ecosystem. It's not only hardware. 1 year we get new GPU generation that gives the performance gain, but at the same time, with same GPU, next year you will see further performance optimization with the ecosystem development, their software, their libraries, and so on. So that is where the NVIDIA's computing platform. Now we are not only the infrastructure, we are providing the platform where one can use those available platform, SDK, and new softwares in their day-to-day computing, right? And this is being used across the domain, and particularly AI, where the GPUs are being used most significantly, right? So let's come directly towards the today's topic of interest, where the climate and weather. So NVIDIA is focusing on earth science domain, and we are trying to work in all three domains like climate, weather, and ocean. The objective here, if you see with GPU, is one is to increase the resolution, and second, reduce the execution time. So we can have proactive actions in case of disaster and any other requirement. And third, sometime which we are experiencing, because of these things, high resolution or execution time less, we could see more stuff in the more into the modeling, which we could not see before, right? So GPU enables that we can go deeper into that and understand more physics, right? So this is the list. These are the HPC models where these are GPU enabled. This includes WRF. This includes Gango model, which is coming up from UK Met Office. I already discussed MPass, and there are so many models. These are GPU enabled. They are in collaboration, work is going on, or mostly in advanced stage with that, right? And these are not limited. I am showing only a few of them, but there are many other models work is going on. And this is towards HPC side, right? Now I will come towards AI side, that what is we are doing. What we look for as a model prediction component, as Dr. Anank in beginning mentioned, we need to have observations. There are multiple observations, those needs to be combined, and we keep them in the category of data simulation, right? There are also significant chances of various kind of formats of data is there, and those need to work. So that is pre-processing has to be done, right? Then we have the dynamical component. There we have the we use the fluid dynamics equations there to resolve the dynamics. Then we approximate the process using the parameterization techniques, and then we look for time integration, right? These are the broad categories we are dividing all process of that. But in each stage, you see there are different kind of challenges with the say observations. They are sometimes incomplete, they are not validated, they are very sensitive. If we change little bit observation, their in initial conditions, they result in different results, right? So they are very sensitive. There is a chaos around that. Then the observations, many times satellite observations are not there due to cloud and so on, right? Then of course we need the solution to be in time. We need that should be more accurate. So, and that should be in time so that it can be used for proactive actions, right? And then finally, there are finite resources for to represent or to visualize the solution. Sometimes those are not enough to understand the process, and those are the big challenges. And that became the forecast or understand the climate change difficult, right? So that's where the AI came to rescue. And if you see in this, AI is being used in all the stages of our system modeling, be it collection, be it simulation, dynamics, parameterization, because we have the data sets now. Those are being used now. The deep learning techniques are being used, and that's where AI is helping in that. So with the deep learning techniques, we are and AI availability, AI libraries and all, and with the GPU acceleration, we are having the new capabilities to apply those techniques in the each part of this say detection, tropical storm detection, translation, transforming from one domain to another, which is, for example, FFTV use, right? Those are becoming faster and those are possible now. Sometimes our satellite images are not accurate or missing, so we can look into slow motion and we can enhance there. Then the parameterization, of course, we have so much data and those are being parameterized based on data and that is being used, right? So coming back to that weather company example, they use around 50 to 150 models for ensemble forecast. And there sometimes they give the weight factor also based on AI, which model will come into, which model will get more weight. Then they use the parameterization technique also based on data and so on, right? So when data is available, then one can look for, and with the deep learning techniques and with the availability of acceleration with GPU, now many things are being explored. These are the few examples. What we are doing, the detection, if you see now, tropical cyclone detection is also possible through AI techniques, which is very commonly used. Translation, as I mentioned, there is a we use that for data simulation, forecast verification. Sometimes that is being used for model intercomparison as well. Prediction, we make a parametric forecast. We use we change little bit in initial condition. Then we do the uncertainty prediction that is required, particularly in disaster management or insurance side, that what would be the uncertainty with our forecast. So that is being used, there also AI being used. I said the observations, initial conditions and repairing the frames and also that enhancement being used. Similarly for emulations, that is across the like physics, turbulence, radiations. And then last but not least, the parameterization, there also the AI techniques are being used. So now I will share few examples of each one, each category where the research paper has already been published, and that will give that how these are being used. So emulation is one of the objective here is we know that few processes in the model, they take significant time. And every time when we do that, take the compute part, it takes significant time and that delays the solution, right? So what we do is we keep all the scenarios. We know that what will be the input range of input, and we keep those data output for that input stored in a file or database, right? So no need to compute. Whenever the model would like to have output for a given input, that is already available. So in real time, there is no compute, right? And that saves significant time. So this is being published. Super parameterized E3SM radiative transfer, and they compared the results and found this is very much useful, right? And this is gave that around 10x speed up. So this is one of the example here. Similarly, for this is the parameterization technique using the resolution of data. This is being published by Yuval et al. And here, if you see, the first is the mean precipitation, and even using high resolution model that was not accurate, but using the AI technique that gave them better resolution of the mean and extreme precipitation. Similarly, this paper is being published for using IFS model, and this is using satellite data, and this is bias correlation and the correction on the bias correlation, and they found that using the AI DL techniques, the bias is improved, which my earlier speaker also mentioned about. The last but not least, this is data-driven ENSO modeling. So here, if you see for ENSO forecast, different kind of models being compared here. And this is the horizontal is forecast lead months. If you see this red line based on CNN, this is again deep learning techniques. Their forecast is much better, and that goes for lead months up to 23 or 24 months, right? and that is much better than much better correlation than any other model. So this is being used by to reconstruct the missing climate information. And here the author was our David is from NVIDIA. They work together. And here, if you see that using this Kriging and PCA, that gives the better output, like output reconstruction as well as output composition that is better using these techniques. And they compared original ground truth versus what we get the output, and that gives the better results with these. I'm not going in this, but this article is in Nature Geoscience. I'm not going detail of every article because that we can take offline. Just would like to give a glimpse that AI is being used across the globe in various forms, and that is helping researchers to focus more on the output and get the better output in time. In last now I will have 2 more slides, and where would like to discuss where we are heading as an NVIDIA and what new we are doing. So these DEAR techniques are being implemented in model. Then we realize that sometimes we have the data and we use those data. They are not following the physical laws, right? What we have in our like equation of continuity, motion, and so on. Those are not being followed. And that's where we came up with a new framework called Modulus, which is based on physics-informed neural network. This is being used across the domains. So that where we have enough data, those are using this framework because, and then we get the physical equation bound the solution, right? Physical governs the equation bound the solution with that. And for weather, we came up with the forecast net that is part of Modulus only. And there also paper is published in 6 months back, which give the better accuracy using forecast net. So this is the framework where we are now focusing more and would like to have more and more collaboration on that, right? And then further to this is being used for digital twin, same thing. And then now it is being adopted by leading research institutes. Right side, it is being shown few industries as well as few institutes. They are more CFD, but weather side also, there are many institutes are coming up. And in a few months, you will see the more results on weather side with using forecast net models. The next one is the emerging our presence in the quantum side, where we accelerated all the available quantum framework, quantum simulating framework, like published by Google Circ, IBM Qiskit, and Pennyline, and many other frameworks. Those are accelerated on GPU. It's the same like CNN libraries and other things. Now, with that acceleration and with more capability in terms of qubit number of qubit to be used for simulation like Shor algorithm or QFFT and so on, those are being used, and now those are being applied in weather also to address the various kind of possible scenarios quickly using quantum computing frameworks. So there also you will see now more research published with NVIDIA. So with that, I would like to conclude. Maybe I hope I am in time. Thanks for giving me opportunity once again. Thank you.
Thank you very much, Dr. Manish. That was a very nice, very informative talk. So next we go to the next speaker, Dr. Advai Mitra, on deep learning based regional downscaling. Dr. Advai.
Hi, am I audible?
Yeah. Yes.
Okay. I will just start and just give me. Is my screen visible?
Yeah, it is.
Okay. So, good afternoon. So, good morning, everyone. And it has been a privilege listening to all the speakers who have been talking about like how machine learning and artificial intelligence can benefit in various problems related to the modeling of climate and so on. And one thing which we have heard repeatedly from several speakers is that like numerical weather forecasting or this dynamical weather or climate modeling they need to work alongside with AI/ML techniques. So, like in my talk, I will speak about one particular application, namely the downscaling of precipitation, like using machine learning. So the main purpose of this downscaling is that we like as already been discussed, most of the climate models, they divide the Earth's surface into grids, and they carry out the simulation of the climatic variables at the grid scale. But the problem is that in many cases the grid scale is rather coarse. Like earlier, in case of several CME 5, when we had there were several models which were operating at about 2 degree or 2.5 degree special resolution. Now it has of course improved to 0.5 quarter degree, half degree, and so on. But in any case, we would in for most practical situations, we need more fine-grained simulation of rainfall or whatever is like variable we are simulating. In this case, we are going to focus on precipitation. So the aim of downscaling is, say we have the estimates of a particular variable at a coarse spatial resolution, and we want to, using that as a basis, we want to estimate it at a much finer spatial resolution. Say let's say we have at 1 degree resolution, and we want to go at half degree, quarter degree, or even finer. So this problem of downscaling, this has been carried out in two main ways: the dynamical downscaling and statistical downscaling. Now, yes, by statistical downscaling, what we mean is we instead of actually trying to model the process like at a grid scale or at a fine resolution, we simply try to estimate some kind of statistical relationship of the variable from the coarse scale to the finer scale. And earlier, that this kind of statistical relationship, it used to be parametric, like it was based on, say, probability distributions and so on. But for the past few years, AI/ML techniques have been taking over, and the idea is to come up with some kind of a machine learning model which will take the coarse-grained data as the input and produce the fine-grained data as its output. So several now what kind the question arises in what kind of AI/ML model it is going to do, and how exactly will it be able to map the coarse resolution data to the fine resolution data, because at the coarse resolution we may have less information than the fine grain data. So how do we kind of create that extra information? So obviously we cannot create something some information which is not there. So we will have to look for patterns within that coarse-grained data itself, and try to somehow adapt those patterns to estimate what the data can look like in the finer resolution. So here is for since 2017 or so, there has been a sequence of papers which have tried to do this. It started with the starting point was something known as image super resolution. So this is not related to art sciences at all. Rather, this is related to computer vision. So here the aim is that we have an image, maybe a low resolution image, something like this, and we just want to sharpen the image. We want to make it high resolution. So for that, in 2014, this paper came out called Super Resolution. So this was the time when deep learning was had just become a very hot topic, following the path-breaking work of AlexNet, which came out in 2012, which showed that the power of deep learning, especially in computer vision. So the special kind of neural networks that was very found to be very successful, especially when dealing with images or any other data which has some kind of spatial structure, is the convolutional neural network. The concept of convolution is, of course, something which was known to the signal processing community earlier also. That is where you have something like a kernel or a filter which you convolve with the image. That is to say, you just translate the filter all over all along the image, and at every location the filter basically tries to identify a particular kind of pattern, whether a particular kind of pattern is present or not. If it is present, then the filter gives a strong response. If it is not present, it gives a weak response. So that way, we actually are able to identify the presence of a particular or any particular kind of pattern within the data, which the image or whatever data we are looking for. Now, so like one particular model that was used for this so to develop this for the super resolution problem, that is for the mapping of low resolution images to high resolution image, that was this SRCNN. SR stands for super resolution, and as CNN suggests, convolution neural network. So in case of CNN, what happens is that instead of having just one single filter, we have actually a sequence of filters, and not once but in multiple stages. That is, we have the initial image, we convolve it with a set of filters to and so we get several for each of those filters we get one output or response image. So we stack all those response images together. Then again on these response images we run another round of or another set of filters again, and so on and so forth, and until we finally get the output. So like with the number of layers of filters, that is of course that depends on the users, depending on how deep we want to build the network. So so basically the what is happening in this super resolution is that like we are looking these filters are looking for some kind of patterns in the low resolution data, and they are trying to like import those patterns like at a smaller scale. And that is the whole idea, is that these patterns repeat. The patterns that are present at a higher resolution will also repeat at a lower resolution. Now, this is an assumption which may or may not be correct in different circumstances, but in most image related tasks, this approach has given us very good results. So now because the when we are dealing with rainfall data or some or for that matter any other weather data, that is also like image, that is spatial data in so each instead of every pixel we have every grid box. So this is like, let us say this is the rainfall map over at 1 degree resolution, which is low resolution all over India. So the intensity of every pixel in this case refers to the amount of rainfall on a given day or whatever is the time step at that particular location. Now now this set of authors, Vandal et al. Into the 2017, and then also some folks from IIT Pune also tried out this approach, and they actually carried out this SRCNN based approach to carry out this interpolation from this from low resolution of 1 degree to high resolution of quarter degree. So like basically the same patch based like so image patches were extracted, and then in each image patches the super resolution process was carried out through so these feature maps were used basically. So whenever we carry out the convolution, we get the result, the output of the of each convolution is feature map. So we carried out this. So this was these in case of SRCNN, this process was repeated like several times to finally get the high resolution data. So that gave some amount of improvement. And there was a follow-up to this SRCNN, which is known as the deep statistical downscaling or deep SD. So in this case also the aim was same, but instead of one round of SRCNN, two rounds of SRCNN were used. So the first round was to the first round in this case was like the input was 1 degree spatial resolution and the output was half degree. And in case of the second SRCNN, that half degree resolution, which was just created, just estimated with the first SRCNN, that served as an input, and the output was quarter degree precipitation. And of course, we can just continue this process by adding another SRCNN after this, and to get finer and finer resolution. So, of course, those have not been tested because of the lack of ground truth data. That is, we have that is at least in case of Indian rainfall, we have the 1 degree data set, which was earlier used. After that, now we use the quarter degree data set. Now station level data is also available, but based on that, like it might be possible to build even finer data sets than quarter degree resolution, but that to the best of my knowledge is not yet available. So that's why we have not gone further, because we could not be tested. So and these SRCNN based model can actually benefit by adding the as auxiliary information the topography of the model of the region. That is, instead of just having the rainfall values at low resolution, what if we have the because the like when we are dealing with small regions, as which is what happens when we are dealing with at a high resolution, then there can be some subgrid level processes coming into play, which are missed like when in the low resolution data. Now these subgrid processes may or one of the reason why that can happen is due to the presence of topography, say the hilly terrain and so on, which we know impacts the rainfall intensity. So like providing this topography as auxiliary information can help in the process of downscaling. Now, apart from this SRCNN and deep SD, there have been further efforts at using deep neural networks for the downscaling of climatic variables, especially of precipitation. So one model which I think Manmeet also talked about was the UNet. So UNet is a structure which was originally used for image segmentation. The whole idea is that we first have a start with an input image. We pass it through a sequence of these convolutional neural networks. At each stage of the convolution, the image becomes smaller and smaller, and finally we reach some kind of a encoded form of the image. So it's not that we are throwing away the information. Some information we may be discarding in the pooling layers, but in the it's like when we are doing the convolution, we are basically at every pixel we are searching in the neighboring pixel, and all the information from them we are condensing and or we can say we are coding and replacing at that pixel. And so finally after all these sequence of convolutions, what happens is this part is known as the encoding part, and the result is a small image in which all the info or a large part of the information is succinctly encoded. And then followed by this, there is a decoding process in which we actually, from that coded image, we actually create the output image, and that output image can be in whatever resolution we want it to be, which can be, in this case, it will be a high resolution. Now, so this is the original UNet idea. The thing is that when we are carrying out this encoding by repeated step of convolution and max pooling. Now, when we are carrying out the max pooling, we are discarding some of the information. But when we want to, like if we want to do something like a segmentation of the image or some kind which is often done in computer vision, that is fine. But in this case, we do not really want to segment the image. Rather, we want to create a high resolution image. That is, so for that we do not really want to discard the information. So which is discarded in the pooling process. So what is done in this case is we add this concept of skip connections. What these skip connections do is that whatever is the output of the neural network at any of the intermediate stages is passed on by a shortcut to the subsequent stages. So like here, as you can see, this is another similar network, known neural network by YNet, which was also proposed for the same purpose of downscaling. It was by Liu et al. It appeared in KDD conference 2020. So in this case, like these skip connections are utilized in the encoding and the decoding parts. The idea of these skip connections is that it provides more information to the decoder part for the reconstruction. That is, the decoder is basically taking the coded version of the image as input and creating the high resolution image as the output. So when it is doing so, like when this high resolution image is being created, of course, we want like we want to remove sorry, we want to like we do not want to discard the information which we had in the original image. So we actually import those information back in the decoding process with the help of these skip connections. And having these skip connections also help us in the process of estimating the weights of the neural network when we are doing it by using gradient descent or whatever. So in short, this the idea that was found in these two papers, Shah et al. 2020 and Liu et al. Is that these skip connections are generally very useful in this particular. Now, based on this, like in my lab, I along with my PhD student Shumanto Mishra, we came up with another alternative architecture. Now, instead of doing the encoding decoding framework, what we did is that we first took the like low resolution image and just first of all just upsampled it to the target resolution by a simple linear interpolation. Like this is there is nothing, no machine learning involved in this. So this is just to take the input to create an initial estimation of the representation of the image in the target resolution. After that, we now the neural network now comes into play. So here we have two blocks of the neural network. In each block, there are again convolutions and skip connections. So, like as already discussed, this convolution helps us to take the neighboring pixels into, or in this case, the neighboring grid locations into account, and hence and encode that information at each location. That is done by the convolutions. While we also discussed about earlier that skip connections are very useful in this case to for the process of reconstruction.
Dr. Advai, you have 2 minutes.
I'll soon wrap up. So, like in the by this process of skip connections, we by this process of sequential convolution and skip connections, we are able to take the image. I mean, the image was already in the target resolution. We now are able to improve the representation of this high resolution image, and the results we have checked on Indian rainfall, Indian monsoon rainfall daily scale data, as well as continental US. And we have, instead of focusing it on all India rainfall, we have also focused it on specific extreme events like some cyclonic storms, deep depressions, and etc. for the period of 2013 to 19. And here are some of the results. So, like these are some of the metrics by which we can evaluate the performance. So we already have the high resolution data in this case, the quarter degree rainfall, and so like we can actually compare the high resolution true high resolution rainfall as available, and also what we have been able to estimate. And in the using the different methods, and we find that like the proposed model that is giving the best accuracy in terms of all these things, the root mean square error, the peak signal to noise ratio, the correlation coefficient, self similarity, and so on. I mean, the worst performance is of course given by simple interpolation. Then as we use the different neural networks, we see a steady improvement of performance. SRCNN is often found to give good results. Deep SD also does well. In some cases, UNet also does well. But in according to all these matrices, the proposed model is found to be giving the best results, not only for the entire all India rainfall, but also for the specific extreme event. So right now we are trying out a few further ideas to improve this. So one of them is like we have, these are the rainfall maps which we have. These are not standalone maps, right? These are like we have a sequence of maps. So that sequential information be used somehow to make the downscaling. So earlier there have been some works of statistical downscaling using LSTM, where the sequential information they have tried to use, but that was not really using the image super resolution methods. Now right now we are exploring if the sequential methods and the image super resolution methods, if they can be combined together to improve the the downscaling. And further, if we can use the different auxiliary information at each location to like for this process, as already mentioned, like in case of deep SD, the topography is used for as auxiliary input. Now we are seeing if some other climatic variables or say temperature or anything else, they can be used with something which is already available at high resolution, if we can use it auxiliary information. And we are also checking if this model can do well in other parts of the world. So we have apart from India, we also have encouraging results from the continental US regions. Right now will soon be trying over the European region also. So that brings it to the end of my presentation. So thank you.
Yeah. Thank you, Dr. Advai. Now we move on to the panel discussion. Some of the panelists have volunteered to give talks, but so let us, and some of them will be just discussing. First, we'll start with Dr. Swapna Panikal.
Good morning, all.
Good morning, Swapna. Yeah, so one specific question that comes to me, you have done a lot of work on sea level and extreme sea level. So what are your thoughts on, and you have also heard about improving the models and use of these new techniques. So how would, because their impacts are going to be very profound, especially the coastal sea level rise. So you can just, so what is your vision for the ESM, how to address the sea level issues at the coastal region? And can we use some of these new techniques for the deriving the information at the coastal sea level rise and extremes? Thank you, Dr. Supra.
Yeah, thank you, sir. Actually, we have seen from the previous talks that AML deep learning methods are emerging field that is having many applications in the climate science. So at CCCR IITM, we are also incorporating the deep learning methods along with the IITM ESM projections to address the specific questions. So one of the application what we can see is to address the sea level along our coastline, because as we have already seen from the talk from INT Garman, everybody is that like climate models have limitations, like we need to rely on the parameterization schemes to address the subgrid scale processes. So that is one way it is introducing the uncertainty in the projections, and also like it is introducing the bias in the projections, climate model simulations. And another is that like we are not able to resolve the processes, like we see the ocean model and all, specifically the ocean grid is, even if we go with a very high resolution model of the global climate models, it will be roughly like 25 kilometers or 50 kilometers. So we are losing the critical information along our coastlines. And another issue is like we have a data like Mumbai and all, we have the sea level data for hundreds of years. But when a cyclone passes along the coast or it makes a landfall at a particular location, so our sensors won't work. So we'll be actually missing the critical information along the coastline. So there comes the application of machine learning or AML. Like we have the model projections, we have the data along our coastline. So basically models can be trained, like we have a relatively shorter span of data. We can use this information and we can understand what is the relationship between the meteorological variables, like how is the winds and how is the pressure gradients. So we can use these methods, AML methods, to train the model. And this can be used to reconstruct the past sea level data. And also like we can also use to understand like what is the projection. Suppose a cyclone is approaching the coast. So how much is the sea level going to rise? How much is the storm surge going to happen? So that is very much important for the disaster and risk management perspective. So these are some of the applications, like we can use our IIT VSM data along with the deep learning methods so that it can be used for the societal application. So that is the step we are going ahead. And we also have a plan to improve the parameterization by incorporating diabatic heating and also like using the AML techniques to improve the model. So these are the steps we are taking at IITM towards incorporating data learning, machine learning along with our IITM simulations.
Yeah, that's very good. Dr. Swapna, one more question. What about these eddies in the ocean? Because they are also much smaller scale, but they have a very important role, especially in the biogeochemistry, in the production of nutrients, and which are coming from the subsurface. They cause upwelling. And is there a way to improve the eddies in the model, ocean eddies?
Yeah, definitely. Yes, definitely. Because even our IIT MESM, we have a BGC component. So we are able to simulate the large scale features still because of the cost resolution and because many of the oceanic processes, again, we have depend on the parameterization. So we are not able to simulate these like Somali region and all, like there is an upwelling and offshore eddies. So these things of information are very much important, like blue economy and towards those things. So these techniques can be applied, like we have the data, we can use the model simulations, and so we can improve this parameterization. So that is another way, like how we can improve our own simulations and we can look more application oriented research on these aspects.
Yeah. Now also the satellite data, you have a huge amount of satellite data of the ocean color, the ocean eddies, and also sea level altimeter data is there. So that knowledge, that information data can be used to improve the models using these techniques.
Yes, definitely, sir. Yes.
Yeah. Thank you so much, Swapna. If there is time, we'll again come back to you. And,
Sure.
Yeah. So we have the next next panelist, Dr. Shaktivel Sami. Dr. Shaktivel, good afternoon. So would you like to make a presentation or?
I'd like to discuss, rather.
Okay, yeah. Please,
I'm not in office. Yeah. I'm not in office. I'm at home.
Okay. Okay, Dr. Sami, yeah. So you have done some work on the polar region, the extremes in the Antarctica and other places. So you can, and also your interest in data-driven science. So what is the potential of these new techniques to, because the extremes are going to increase with climate change, extreme precipitation events, extreme weather events. So how would you like to use these things to advance our predictions of extreme weather in a changing climate?
Yeah.
Over to you.
So I would like to see like this. I mean, number one, if you look at the earlier scenario, we don't have much kind of collection of data.
Okay.
Now, the present scenario, we have a lot of observations. I mean, if you look at, we increased the observations to collect the data, that is called institutional data or satellite data. And many aspects we have been collecting more and more amount of data. So these data are coming into, I mean, multiple ways the data are coming in and stored. So we call it as a big data or whatever we call it. The volume, velocity and variety of huge amount of data is being available with us. Now, what we are looking for that as a human being, whether we can do, how the data can be, analysis can be done, how we can do data mining kind of things. Now, for that, we need some kind of data mining approach or machine learning AI kind of approach, which can help the scientists, domain scientists. Yes, this could be a possibility. These are the patterns. These are the patterns exist. Based on the patterns, what can be done? Whether the extreme weather was exist or not exist. Why this kind of patterns repeatedly is happening it. Otherwise, we are fully depending on historical data. Now, based on the AI and ML tool, particularly data mining and data warehousing approaches, which will help us to say that, yes, this was happened earlier, this may happen next time. And based on that, we can come up with a deep learning, machine learning models. So the same approach we have used for blizzard prediction, that is a special phenomena of weather conditions, which happens in Antarctica. So what happens, I mean, the visibility will be reduced a lot. Suppose you want to do any kind of station operations, or you want to go for field work and data collection kind of things, it is very difficult to move out because the whiteout will be there, snowfall will be there, heavy wind speed will be there, then visibility will be totally cut off it. So those kind of scenario, if you want to predict, so that the station surrounding the station, they can do the operation whenever they want it. So this kind of information is very, very essential for our, not only scientists, those who are going for technical people for operation purpose and data collection things. So the blizzard prediction is one of the major events. It happens all of a sudden. So those kind of things we want to do that. So we have done a lot of exercise by using various deep learning techniques like ANN, CNN, LSTM used. In that LSTM also, we used sequence-to-sequence model as well as normal LSTM model. We could see that, yes, LSTM is doing better job when you're comparing with other deep learning neural network models. So we have, we ran the models in the IITM HPC system. We could see that, yes, there is a significant output has been received. And we are, we could able to see that the results are much better when you are doing this kind of things. Now, the problem is particularly the Blizzard data availability, collection of data, it does not happens every day. It's a basically seasonal based kind of events. So we need to collect more and more data. So this is only research model, whatever we have developed it. We need to, when you want to become operational model, we need more and more amount of data to sustain that, yes, this could happen like this. So for that, we are in the second stage. Research model has been finalized. It has been working fine. We are going for the operational level. If it works fine, then we can roll out saying that, yes, this could be happen like this. So Norway, they already started this kind of approach. We wanted our own data, our own station people. We should inform saying that, yes, this will happen. And you please don't move out from the station. You do activities, indoor activities. Whenever you want to go, this kind of forecasting could be done, particularly for blizzard predictions.
Yeah, thank you very much, Dr. Sami. Now we go on to Professor Sridhar Balasubramaniam. Dr. Sridhar, we know that you have done a lot of work on the weather dynamics, on the climate dynamics, and you are using these data-driven techniques to forecast. And you're also a co-founder of this company, Weathercast. So we would like to know your views and thoughts how to improve model predictions of weather and climate using these new techniques.
Yeah, thank you so much, Dr. Krishnan. First of all, excellent talks by everyone, and I'm just going to take the conversation, whatever they had presented in the talks, forward as a panelist. So I would like to kind of split my answer to your question into two baskets. One is the science aspect, and another is the product aspect. So when I talk about science, it's about understanding the processes. It's about for instance, we look at very science specific processes. Let's say jet stream, how the jet stream undulates. What is the temperature gradient between equator and pole, and if that is changing, then how the jet stream pattern changes, whether it becomes stable or unstable. So those are the scientific questions, and of course El Nino, how it changes over the period of year, over a 5-year period, 10-year period. Those are the scientific questions. And then when it comes to weather and climate, then there is this product aspect, which is just three things, which is when, where, and how much it will rain. That's all. I think when it comes to product, the science aspect takes a backstage, and when you are trying to talk to someone, even let's say an individual or a business organization, then they just tell us that, okay, we don't want to know what is the complexity related with weather. You just tell us when it is going to rain, where it is going to rain, and how much is it going to rain. So these are the two different aspects, and to connect them is the main challenge right now, and that is what we are dealing with, to be honest. Ayantika gave a very nice background of how these models work and what contributions we have made in terms of scientific progress. And of course, the geophysical fluid dynamics field has evolved so much that we have a very good handle on the processes, the large scale processes, especially, like we know what are Rossby waves, what are Kelvin waves, and how they affect the El Nino patterns. Or we know the jet stream, and we look at that evolution, and we can figure out, okay, it's going to become unstable. So that means it is going to pull down the cold air toward tropics, and it is going to take the warm air towards the mid latitudes, and that's how you get these heat waves and cold waves in regions which are not used to getting those in the past, right? And that requires a good knowledge of your geophysical fluid dynamics terminologies, equations, understanding the vorticity deposition and all those things. And we have made a lot of progress in that over the past 50, 60 years. When weather forecasting started, it was using maps. Like people would take the meteorological maps and they would look at these patterns of pressure and they would make conclusions. Meteorologists would make conclusions. And slowly we have now these numerical models which have been developed based on the equations that have been evolved from basics of fluid mechanics, atmospheric ocean dynamics, and geophysical flows. And slowly those are building up. And like Manish talked about, the resolution is very important, and that resolution aspect has made a lot of progress in terms of coming up to regional scale modeling. But the one thing that is still missing is we are not able to characterize the turbulence. For instance, we still have to parameterize the turbulence, and that is one of the main aspects which is missing in the models. Like we can't, even today, we can't actually resolve the turbulence processes which are of the order of less than 1 millimeter, even at a cloud scale or even at an eddy scale, which you brought up in the ocean. And it is so the thing is we cannot run a direct numerical simulation. DNS would resolve everything, but we cannot do that because it is computationally expensive and it will take years for it to run and give an output. So that's why we stick to these kind of parameterizations. And the issue is parameterization is you don't know how it will work for a given region. Okay, they are very region specific, they are very process specific. So over the years we have been able to take some processes, take them to the lab, try out some experiments, try to say that this is the parameterization which is suitable for this particular process. So go test it in the field. If it is expandable, then put it in your model. And that has been done, and it is going to continue, and that's how we are going to improve the scientific efficiency of the models. And I think that's already IITM is doing that, and I think it's doing a great job of that. So that's required because only when we have these robust weather models or robust climate models, then only we can actually science-based predictions can be given out. I think we can rely on them because those are fundamentally sound science-based outputs, which tell us exactly what is the trend. So the trend will be is going to come out from the science. Without advancing the science, without advancing the parameterizations, we will not be advancing in the scientific aspect, and we will not be understanding the trends that are coming in the future. So that is the scientific part. So the improvement in the parameterization is something that our group is also doing at IIT Bombay. We have been trying to do a lot of experiments on or field processes on trying to improve the entrainment, which plays a very important role in cloud processes, or trying to understand the mixing in the ocean. How much cold water and hot water mixes, because that is going to tell us how much the mixed layer depth is, and then how much heat is being transferred to the atmosphere and all those things. So that is at that level. Now coming to the product level, this is something in my journey I realized that I was only focusing on the science, but then when I was talking to some people, then they were like, yeah, this is all, whatever you're doing is great, but still we are not able to tell where it is, how much it is going to rain and when it is going to rain. Where is going to rain is something which still we can say, because a low pressure system is a big system, and we can tell that, for instance, a monsoon, as soon as the monsoon trough shifts to the foothills of Himalayas, then we know that Northeast and Uttar Pradesh and North India is going to get rains. But still the question of when and how much, that still remains. And that is something where this data-driven techniques that Manmeet and others, Ankit and even Mitra, these three people mentioned about the AI ML techniques. And that is going to help us because we have a lot of data, and we take the data, we smartly process it. We just don't process it, but we smartly process it with involving machine intelligence as well as meteorological intelligence. Like we shouldn't just blindly do the machine intelligence. We also have to take cues from meteorology, like, okay, at what levels these processes become important, and try to fit into the data science framework, and then go ahead with improving the predictions, and on a shorter scale, let's say 24 to 36 hours or maybe 48 hours. And that may help us in answering to some extent the question of when, which is the temporal aspect, whether it is going to rain between 3 p.m. and 9 p.m. and how much, whether it is going to be 100 mm or it's going to be 5 or 10 mm. So that is the connect which myself and my group at IIT Bombay are trying to fit in together, where we are looking at the scientific aspects on improving some of the model capabilities, which of course we don't do the operational work. It is up to IITM and IMD to do it, but we do the science aspect there. And then for connecting the product aspect, that's how we started our company with the help of a couple of students from IIT Bombay who were PhD students. So they did some work, and we decided to start this startup, which is called Weathercast Solutions Private Limited, where we are trying to link the two. And the product is basically, if we can tell them when, where, and how much it will rain, and if we can be, at least if we can improve the accuracy by even 5 to 10%, then I think it will be useful for the common public and for farmers, for agriculturists, for businesses, and all those people. So that is how I am looking at this particular thing, and that's how I feel like everything will fit in together: the science, the data science, and the data. All these three aspects will fit in together, and hopefully we will definitely have a much better framework in the next 5 to 10 years, is what I believe. So yeah, thank you.
Yeah, thanks a lot, Professor Sridhar. I think you have very lucidly explained. One is understanding the science part, focusing on how to improve the parameterization and those aspects, and another is the product generation, which the public wants. And these two, and you're also trying to link the two, not just let them go in two separate directions, trying to understand the linkage and how to improve the models in turn. Yeah, just I had one question. Because there are so many time scales, even when you're looking at a very small region, you're trying to understand the variability or the extremes in the precipitation. It may have remote teleconnections, as nicely brought out by Ankit. So there are multiple scales involved. And so which means that, and it's a very nonlinear system. So the amount of data that you need to, even if these models are going to predict this artificial AI/ML techniques, the amount of data that you will be requiring is enormous. So that's one of the issues. How are you going to deal with that?
Yeah, that's that's a very interesting and a valid question. So the amount of data is going to be that's going to be needed is huge, and that's why we depend on the data which is already coming from the network of ground stations that we have. I think the government has, and then the satellite data, which you rightly mentioned. The satellite, and we have these. I think in the satellite technology as well, we are a lot of startups are there which are planning to put satellites into the space, and these are going to be hyperspectral satellites. So they have the capability of trying to survey a specific region. So the satellite information assimilated into a meaningful data combined with the ground data, and of course the data coming in from the weather models itself, and maybe some other source of data which at the moment I'm not, buoys, of course, right? Ocean buoys and all these things. So these are the data sets which are going to help us in creating a repository. And one of the things that the vision that we have as a part of the startup is to increase the number of weather stations that we can have over India, so that right now we have 4,000 or 5,000. Like, and US has close to 300,000 weather stations. Of course, those are not all government; those are personal weather stations as well, like from hobbyists and all those people. So if we can improve the ground network and combine the satellite data and all other sources of data, I think we will have at least good amount of reliable data set, and quantity should be enough to have some impact in the machine learning AI kind of in that aspect. So that's what I feel.
Very nice. Yeah. Thanks a lot, Professor Sridhar. That was very nice. And now we have Dr. Praveen Pankajakshan from Cropin. I would appreciate if you can give Praveen can give us some insights about the applications, agricultural applications, use of these new techniques, especially in a changing climate. Dr. Praveen, over to you.
Thank you, Dr. Krishnan, and other esteemed panelists as well, and speakers. So I have to maybe, I don't know, when I thought about, this particular day, I was wondering actually like how to present the work that we are doing also in Cropin. So we come from the other side, and I also wanted to maybe give a brief highlights on what we are doing actually, and the implications of climate change, and also modeling. I've been listening actually very intensely to all the conversations around the models, weather models. So we have both, weather and climate long-term normals, which we use in our estimates of crop production, and also on climate change related behavioral change of farmers. So I come from the other side, and thanks so much for inviting. I just maybe want to give a glimpse because I don't know, because I'm from the other side, maybe it might be hard to visualize as well. So if it is okay, if I can share a few
No
slides.
problem. And sorry to keep you waiting for such a long time. Yeah, please go ahead. I think it will be nice to hear from you. You can just go ahead with the presentation.
Sure. Let me know if when it is visible. How much time do I have? Because this is
yeah, no problem. You can take 15 minutes. If we are late, no problem. You can take 15-20 minutes. It's okay.
Okay.
Then we can wind it up afterwards. Yeah.
I'll try to make it more interactive. And maybe in the interest of time, I'll also be very conscious of the other speakers' time as well, and maybe go into some of the details of recent, AI models that we have been building as well. So as I said, we actually work mostly with farmers and with agriculture institutions, organizations, development agencies. So I represent Cropin, so I'm currently the VP Data Science and AI within the Cropin AI Labs. And we are a small group of about 20-25 mixture of earth observation, data scientists, agronomists, trying to solve some of the most difficult problems in agriculture using satellite images, ground collections, field collections, and also using AI techniques, right? Recent advancements and also the classical ones. I come from the classical machine learning approach, so with a lot of foundational knowledge there. And of course, I will share with you some of the recent advancements that we are also doing in this space on, the deep learning space. Just to give you some idea is that we have been working, also a lot on working with farmers on climate resilience. For example, this is one project with the World Bank, and mostly working with Bangladesh and Sri Lankan farmers on climate adaptation. So what we do is we ourselves don't have weather models, so we have to depend on weather models, provided by others. But we do actually evaluate many of these weather models. So we have like a fair connections to all of the weather models that's both private and publicly available. And we use that actually mostly to provide package of practices, advisories, weather advisories, sowing time, harvesting time, related to pest and disease, early warnings. Those are things in which we actually provide, intelligence to farmers as well. But to do that, I just want to also, so this is the entire space that we actually cover. And the way that it happens is very briefly is that we have two major platforms, the Smart Farm and the Smart Risk. So for the last decade or so, we have been digitizing farmland. So so we have apps and and also the platform to scout a particular farm, draw the geo boundaries, and then that can be brought inside our platform, and it can actually be monitored, right? So we have been doing for millions of farmers across the globe. And that is a smart farm. And once it is actually like a geo-localized and the geo boundaries, geofencing is done, then we can actually monitor that. We can detect the crop, we can predict the yield, we can give an idea of within the season how the health is, what are the different kinds of stresses, biotic and abiotic stresses, nutritional deficiencies, we provide advisory on irrigation and what based irrigation, scheduling irrigation, excessive or deficit of water, those are. And I also, one major application is also on disease early warning systems. Apart from that, also our recent work on sustainability on carbon and deforestation, right? I'll maybe so today's talk is more on crop identification, and my contention to that is that is really the most critical element to do if you're looking at India-wide, right? And if you are able to do crop identification, then the others would follow through. Then we can actually like go back and solve for other problems as well. And I'll give you a glimpse of, very, very briefly on why that is really important, right? Because you have to understand that there are other models kind of like depend on top of this, and not many organizations have an ability of identifying this reliably. So that becomes a very important piece. Now, one can actually understand, right? Once we identify the crops, then providing yield. Without crop, you can't provide yield. Now, you can't provide harvesting information. When is the right time to harvest? We do have like weather information coming in, but the right time to harvest is dependent on all of the right, not only the right conditions, but weather conditions, but also on what is the underlying crop that is growing. Now, there are other elements also which are important, and I can give you an example. A few weeks back, we were actually like visiting some cocoa farmers in Kerala, and we actually, after a day or two of interactions, we realized that many of these farmers had actually, and I have one slide on that as well, but they had actually, something called as the black pod disease, and you have also some mosquitoes which can actually infest also the cocoa fruit, right? Like, and which can actually lead to production loss. Now, the most important thing is we have actually observed, and talking to the farmers, we realized that that has been more severe after the 2018 floods, which happened. And the result is that, and this year, and last year they had a good produce, but this year, they didn't see the rainfall in March, which is kind of for them an indication of how they are actually going to do as a harvest this season. Now, the problem with the flood which happened is that deprived the soil of essential nutrients. And we actually went and like took some soil samples, and looked at it, and you could see that because it's an agroforestry system, you can see that the topsoil is rich in carbon, but then it's the deeper layers which actually have depletion, and it has actually lost its ability to hold nutrients as well. And all of that is something is resulting also, and when soil is affected, then you can also see it in when the bottom is affected, you can see it in the top, so you can see it in the canopy health and everything. So what we actually have within our system is that we have actually over now it's more than 400 crops and over 10,000 crop varieties. And we have all of these because of the farm digitization that we've done over a period of time. This is all within our platform. And now we can use this to train our data set. So many of our earlier speakers were also talking about AI and, and also about deep learning models and machine learning models. So for those familiar with it, you will know that how challenging it is to actually train these models with minimum amount of data sets. So they are actually very data hungry. So this is something that we have, and we also have like both paid and openly available Earth observation satellite data, both high resolution and medium resolution. So we combine all of that, and we solve for some of the critical challenges. So I'll talk only about one of them in the interest of time, and I'll also be very quick in it. But this is just for, also to seed some thoughts as well, because this is something that we see every day. And I actually was not conscious of the fact that while a lot of, we are aware of the implications of climate change and everything, I actually was not aware that it is visible, today. So the farm visits and everything helped me understand that even at farmers, they are actually able to perceive that it's not the same anymore. And so the way that they are actually growing, when the visit that we had was an agroforestry system. So cocoa is not the only thing, right? They have other crops also which is growing. So when one particular crop is affected, then they have to depend on another crop to provide for their sustenance. And but that particular crop might not actually have the rates in the market that you might expect, right? So this actually, so there is a huge implication also on food security. I talked about pest and diseases. I talked about the black pot disease. So all of these we are observing as a result of both weather changes and also due to long-term, normal. So we see either rain deficits or really high, temperature stresses that's happening at the land level. Now, even as we speak, we are seeing this global, at the global scale, you are seeing the, if you look at the land surface temperature from the space, you see that it's heating up, right? And suddenly we are having huge amount of problems in Europe and other countries as well. And also in insurance claims, this is a very challenging topic as well, where we are working with actually with the government of India and Pradhan Mantri Fasal Bima Yojana projects, and how to estimate the yields and also how to understand if there has been some event and if the the production has reduced because of that, and dispersal and things like that, right? Um, so just changing gears slightly, while we talked about pests and diseases, but I don't know if many of you are familiar, but actually, right now as we speak, many of us are talking about the atmospheric carbon, but to pull the atmospheric carbon dioxide into from the atmosphere and to stock them is actually a difficult challenge. But I don't know if many of you know, but the both the existing croplands, even some of the major croplands like maize, rice, soybean, and wheat can actually be a very good. So we look at farmlands as food production systems, but it's not necessarily only that. I think the paradigm is changing right now as we speak, and we are also looking at croplands as ability for the soil to sequester carbon, and also almost 26 to 30% of carbon stock, soil organic carbon stock, actually is a result of small scale farmers, right? So if you look at India itself, you're looking at, many of the farmers are actually small landholding farmers, right? With an average landholding size of about 1.5, 1.7 acres of land, right? While in some other locations, you're looking at hundreds, thousands of hectares of land, the average size. But even these small scale farmers are actually I would say like planet heroes in a way, because they are accounting for this major soil organic carbon stock. So just coming to the main theme of also my my session, or my something to think about is this whole idea of crop identification. So we have been looking at it from not only from yield, pest, and disease, but also in terms of greenhouse gas emissions, right? And even to do so for a lot of people, maybe it might look like a simple problem, but in terms of AI solving for identification of crops from satellite and remote sensing is a very, very challenging problem, And I don't know if many of you know, but food does actually generate quite a bit of heavy environmental footprint. And how we use land is very, very critical. In fact, the global temperature change can also be associated with how the land use and land class the changes happen, like moving from, because of deforestation or loss of agriculture land to urban spaces, all of these are things which we actually see right now. Now, this is my favorite subject as well, and I'll actually like briefly talk about it. Is that even as we speak, and this is the main area of research that we are focusing on, is that there is limited amount of data that you can actually pull in, right, from any source, from either your private sources or private data repositories, or from public data sources. Then the main question is, so all that we talk about right now is a supervised learning approach where you are given labels of data and you kind of like train your models, either a machine learning model, let's say support vector machine or random forest or whatever it is, so decision tree or convolution neural nets. So you actually take the data and you kind of like ensure that it's the output actually looks like that label format, right? It might be a label, it might be a classification problem, or it might be a regression problem, whatever be it, or it might, you might be using LSTM, or some kind of recurrent neural networks. Whatever be that, but it's all comes to that, you're giving an input data and you have a label, right? And that's not how, if you want to actually represent how human beings learn, that's not how human beings learn, right? So even when we look at this whole problem of crop identification, so I did make the point how crop is very important for understanding the carbon sequestration that's happening in the world, and also for reduction of methane, reductions of greenhouse emissions, right? Greenhouse gas emissions. But then how to actually look at the space-based satellite and use satellite from space, look at the land and how to actually like classify them, right? And by doing this, you're, now it's a very difficult problem to solve because it's you're looking at a very large, diverse data set, right? So this is one idea that we had recently, and we are actually like, a lot of people talked about digital twins. This is something like creating an individual digital twin of the Earth, but from, using satellite images. So you can actually feed all kinds of satellite images. Now, here I have actually fed it with a labeled data set. So this is openly available data set, but we also have our own, unsupervised, like open satellite data set that we can actually pull in. And this is a very simple network, and this is just made as a demonstration, but you can actually like have any kind of, you can have the residual blocks, or you can have, other, inception layers and things that into this particular architecture. But the whole idea is not this architecture, but is that how we can actually take any images and, the usually the way to do it is that you give these labels and you ask it to train. Right now, rather the other approach that we had taken is, and this is the what's the representation learning problem, is actually like break this and look at the penultimate layer before before doing the softmax, and look at the feature vector, right, that is taken. Now, this feature vector in the traditional machine learning, the way that people would do is they would just take these satellite data, they would generate features on top of it. Somebody talked about wavelets, or, both spatial, spectral, and temporal features, right? You could also have like something like your NDVI or some other index that is built, and then you would have these features, right? But with the help of these deep learning architectures, you can actually extract those features and the kind of relationship that you want, both spatial, spectral, and temporally, And those features, you could actually represent them. And now the idea is not to actually like have a labeled class, but actually like take these features, and then you can actually, now this is at a higher dimension space. So to visually represent it, I have actually projected it onto onto a 2D space. And you can see that I've done, this is just for visualization. I used a TSNE, or you can use a UMAP for projection as well. And then you can see that, it has, and I've labeled, because I know the labels in this case, but you might not need to know. You can do unsupervised learning like a k-means or something, and you can see that it's actually like clusters, pretty well, the different colors. And if I go and study these labels, you can actually see that it's the lighter colors actually represent water bodies, and the darker ones, the black ones, is like, river and water body is like separate, because you might have a pond as a like a moving river, as well against roads and vegetation and croplands and forest lands, right? So this is one work that we are looking at. So here is, a larger pictorial view of it. So this is not a supervised learning approach. This is just how it's clustered. And this is how it's learned the representation, right? And you can see that the labels have been separated quite well. Even in we do find this even in a label class, that these guys here, forest, grasslands, and croplands, are most often together, right? And they have like, but the separation that's happening here is still quite significant, I would say. Even from a space, if you look at grasslands and croplands, they look quite similar. So having that separation is very critical. I'll maybe like we also like have some supervised approach as well for crop identification, and I'll just show you one particular I don't know if you're able to see the screen. This is actually the platform, how it looks like. And because, the invitation came from Pune, from IMT, I just thought that IMT, so I thought I'll add Pune here as a comparison. So we can actually study we have done the crop identification for different geographies in India, for different seasons that we can do. So while it's loading, you can see that these are paddy, red grams, groundnut, and other areas which it has detected. And these are also the expected yield that we can have. We can actually go into the details and see, like, in certain regions, for example, it's red gram as against a major crop versus minor crop, net zone area. All of these are things that actually could be evaluated, right? I'll skip through some of them because I'm also conscious of the time. But another area that we are working on is also to use knowledge itself. There is quite a bit of knowledge that is there in agronomy and agriculture, combining that with remote sensing and AI, how to actually distinguish crops. So we have done like across the world yield estimations and things that this was something that we did for rice area, even variety level identification in Bangladesh for Boro rice. This could be actually interesting for the group itself. So this is a recent study. Somebody mentioned about hyperspectral data. Like this is actually from Prisma data set. And we are looking at methane emissions. We are able to identify different, areas like submerged paddy areas. And we are looking at how the methane emissions look like based on this index. So you can see that these have like pockets of areas where during a growing season, because of the decomposition of the biomass and the composting which happens in situ, right? You have also methane emission that's happening, right? So these are things which we can also study. I'll just maybe also talk a little bit about food security and this is probably will be my last slide, and this is a big issue that we actually also that we currently face. Like for example, if you look at this particular region in Nigeria, this actually this area is like also split into different agroclimatic zones. And if you see that this particular, the northern part, Borno, has like a lot of, food stresses, but it also has, the problem with these regions is that it also has a lot of stresses of climatic stresses as well, and obviously this affects the food production here. We did some, taking this crop identification, we tried to estimate the wheat, first identify the wheat and then estimate the yield. And we found that for some reason, Borno, which was earlier a state, which was a state actually like in the northern part, northeastern part of Nigeria, our estimates, our machine learning yield estimates came out very low after wheat identification. And we were actually supposed to be in the top most acreage. And we were actually surprised by this, seeing it, and we thought there is some issue with probably with our modeling for this particular state. But then later on, we found that because of the insurgency, there was a lot of migration that were happening of farmers who were originally growing here, and they were actually moving to the neighboring regions, even into Chad and other locations. So the food production here was actually reducing, So this is something that we also identified, and we are also evaluating the effect of the current war and also the Sri Lankan economic crisis, So I'll stop here, but there is also a lot of work that we are doing and these are, I have to acknowledge also my colleagues who are very much part of all of this study. And there is a lot of work that we are doing, but, I just wanted to give you also a user experience of, both, who are using climate models, weather models, and to understand. I didn't talk about that, but we are also, studying like rice, for example, growing in Nagaland and Kerala, and we see a different pattern. For example, deficits happening in Nagaland and excess happening in Kerala, and using that to see actually how the farmer is growing lesser rice as against more shifting towards more rice, So those are things that we are also studying as well. So I'll stop here, but thank you so much for also giving me this time, and really appreciate it.
Yeah, thanks a lot, Dr. Praveen. Really enjoyed your presentation. You have nicely covered the importance of Earth observations and remote sensing, and you have used all these new techniques, data-driven techniques for crop identification, also methane emissions and food security. You nicely brought out those issues. And now, and first of all, I would like to thank all the speakers and all the panelists for the excellent presentations. Really enjoyed a lot. And now there are some questions in the chat box. Maybe Dr. K.C. Gowda, would you like to pose those questions?
Questions where I cannot see the chat box.
In the chat box, there are some questions, I think, to Dr. Praveen.
Yeah, Dr. Praveen, yes. So this is
from...
Yes. Okay, there is a couple of questions. I'll try to address them. Are you using NLP for knowledge classification? Yeah. So this is Dr. Manmeet Singh. Yeah. So what we do is we actually we have like multiple data sources for where we have like both public and private data sources. So the important thing is like we have all this repository of data. How to actually bring that as knowledge is a major critical thing, right? So first thing that we do is extraction of that data, and through that, and then distilling that, and for all of that is what we are actually using NLP for. We are actually still building that, so it's still in the early phases. Our primary work has a lot been in building knowledge for for actually like augmenting our crop identification and yield estimation, all of that. And so that is actually the major piece of it. So for that, we are actually building also the NLP systems for, and it's still early stages because it's quite a challenging problem. we are looking at knowledge graphs as a basis also to embed these because you have like both crop level information, you have the different yields there, the host plants, the disease that can happen, and different other entities that you can embed and connection between these, right? So we are trying to see if we can build that as a knowledge engine system within us. One is extraction, the other is also building this whole system, right? So that's what the next area of research that we are focusing on. What are the satellite data that are used for crop classification? So we use actually, so for crop classification itself, we have like access to both Sentinel-1 and Sentinel-2. Landsat we use for yield estimation. We are not currently using Worldview, but we use Planet Labs, for example, data high resolution image that's at 3 meter that's coming up from Planet Labs. But in that, so Sentinel has like slightly higher resolution than Landsat, and Planet Labs has more higher resolution than Sentinel. But Planet Labs is, you have only like the 4 bands which are available currently. They are extending it to 8 bands. So we are trying to see how we can use that 8-band information itself. But it's not like the hyperspectral one, like, or even the multispectral one. The 8-band information has like very specific use cases itself. So that's something that we are also trying to integrate. High resolution images, we use also Google Map images, like which is at I think at 0.3 meter, 0.5 meter resolution. Those are mostly for land parcel delineation. So the cadastral map and everything creation, we use that. We have not yet used Worldview 3, but some of the we have to also be conscious of. We mostly rely on open source and freely available data sources because we'd also have to see who can pay for it. That's why we rely on Sentinel and Landsat. For very certain farmers, certain organizations, we have also provided them with Planet Labs where they really want that precision agriculture, right? So we look at that. I hope those addresses those 2 questions. How much it will rain? We need to have rain forecast and range. I interacted with various industry. For them, knowing the range is enough. Yeah. So one thing is like, this is one. Dr. Manish Madani, this is also a great question. So while we are looking at weather forecasting, we took up, multiple different weather forecasting data that's available. So these are available at API. And we did that comparison against also some of the weather stations available, where we know. And what we found is that this is purely from a user experience, and for us, for actually like forecasting, for rain forecasting is important, like to obviously to know that threshold, right? Like, because they want to know if they should go for, some of the farmers want to know if they have to go for sowing, and suddenly after sowing, if there is excessive rain, then the seeds get washed out, so that's really bad. But also to know the, how it's going to progress over a period of time. So those thresholds definitely make sense. But what we have found is there are also like huge differences between what we have, the relative humidity, temperature, all of this, are within the ranges when we look at it from the weather stations, but precipitation is something that there were really huge errors, and we are really struggling with that because when often the forecast can actually go wrong in that. And we are looking at a 15-day forecast, and I know that as you progress in the number of days, it actually also the accuracy decreases. But so we are trying to more, at least for disease and pest early warning, we are more trying to see if we can rely on humidity, temperature, the solar radiation, and those parameters. Rain forecast would be really lovely to have high accurate, but looking at the data set, I feel that researchers are struggling with that. So we don't yet have access to high accurate data sets. So. But yeah, at least like knowing if there is going to be a deficit or excess and also to know in the next few days, in the next couple of weeks, to know that maybe even not a couple of weeks, maybe in the next 10 days to know that would be would also be very useful. Yeah.
Yeah. Thank you very much, Dr. Praveen. I think it was a wonderful talk, and you have really shown a very practical demonstration how this information can be used, and it was very insightful. And also, I want to thank all the presenters and all the participants. Excellent talk we had. Really, truly, in the spirit of iConnect, we had the scientific community, the industry, and they're all coming together. And also, I want to thank all the participants for attending this meeting, and also my co-coordinator of this event, Dr. K.C. Gowda. Thank you very much. And Dr. K.C. Gowda, if you would like to say something, please go ahead.
Yeah, I also, on behalf of DST, CSIR, and MOES, thank you all the speakers and Professor Krishnan also for wonderful coordinating this meeting. And as one of the main objective was to identify and establish the network, I can see today the interaction among industry, government scheme, and all this academia will sure find a path for a long way to go, and we can work together, and that can be a good output of this iConnect event, which was meant for it. Thank you once again to all of you. Thank you.
Thank you all. Maybe we can take a group photo.
Okay. So all can
come. Yeah, Ankit. Dr. Ramana is there. Nice to see him from NRSC. Yeah. Ankit. Okay.
Thank you, sir.
Thank you. Thank you all. Bye.
Thank you.
Thank you. Bye.
Thanks a lot, sir.
Thank you.
Thank you. Thank you so much, Ramana.
Thank you, Dr. Krishnan.
Thank you, everyone.
Thank you, Dr. Manmeet. Bye, everyone.
Thank you. Bye-bye.
Thank you.
Bye.
Thank you, sir.
Thank you. Thank you.
Thank you, Dr. Krishnan. I just went to another class. Maybe if I missed something at the end. For 20 minutes.
Okay, no problem.
Okay,
Yeah.
thank you very much.
Okay, thank you. Thank you, Ankit.
Good, Ankit Agrawal. Yeah.
Thank you, Dr.
Thank you.
Good. Okay, thank you, Krishnan sir. Okay.
Yeah, thank you. Thank you, Dr. Gowda. Thank you so much. Bye-bye.
Bye.